Good afternoon, everyone, and thank you for joining our course, Introduction to Generative Design for Additive Manufacturing. Today, we're going to be hearing from Michael Bogomolny. He is the co-founder and CTO of Paramatters. Michael is a world-recognized expert in the field of topology and multiple disciplinary optimization, generative design, computational geometry, and additive manufacturing, with over 25 scientific publications. I'm Eric Beardsley from the Dynamism marketing team, and I am a 3D printing specialist. On the agenda for today, we are going to get into what is generative design and what is the value to you. We are going to see Michael optimize a part live for us before we get into some industries and applications, as well as a few case studies so you can see the real world results of generative design. We will talk about additive manufacturing and how to use it to manufacture designs. And then we'll finish off with how to get started with Paramatters and get your design 3D printed from Dynamism. And without further ado, I'm going to go ahead and hand it off to Michael.
Today we are going to talk about generative design, and I would like to touch what is generative design. Today, Paramatters, we believe, offers the most comprehensive solution in terms of design, engineering design for additive manufacturing. We offer a very highly differentiated set of capabilities to address challenging commercial engineering challenges. We are not only about creating nice, cool shapes, we're about solving tough engineering problems. And those you can see some of our customers. All right, so let's talk about design. First of all, what is design? And I looked at Wikipedia formulation. What basically design is a creative act of determining product form taking place in advance of manufacturing, of physical act of making product, right? So first of all, we need to create this form, right? And talking about engineering design, industrial design, we need to create a viable shape. When I'm saying viable, it means it should be part that probably should carry weight, carry loads, should be viable in terms of ability to carry weight, not to break under applied loads. This is very important part. So let's look how design is done today for traditional manufacturing. You probably can see in any company, design is done typically by two engineers. One is creating shapes using CAD tools, another one validating if these shapes are viable, running some finite element simulation. And the flow today is that users create shapes based on their intuition. So it's designed very much human-centric because another engineer probably will generate design which looks different. And this short video is showing very well how design is done today. It's basically taking primitives and doing some Boolean operation, very tedious and labor-intensive process. After creating the shape should be also validated in terms of physics, and it's typically iterative process between two engineers. And so this is traditional design, because also I didn't say that CAD was tailored for traditional manufacturing, basically. Now, talking about generative design, I would say there are different formulation and definitions what generative design is. My definition is that algorithm-based design. We at Paramatters generate, our algorithms work based on physics, based on finite element analysis, based on mathematical programming, optimization algorithms. And the way it works, generative design works, that we need to provide algorithm with working volume. We apply boundary conditions, we apply load cases, and we specify our goals. Now, if we change loading conditions, of course, shape will change as well. So as you can see, first of all, the algorithms place material where it's really needed, and it's not human-centric as was. The designs generate fully automatically, hence it's not that labor-intensive, and typically designs much more optimal than manually created models. So And this is like, we go, what is the value of generative design? First of all, the design cycles much shorter. And we at Parameters create, our technology allows generating designs, typically a one-click solution. When I say one-click solution, user defines the problem, clicks the button, the output is fully manufacturable model. If you're familiar with similar tools on the market, they require some going back to iteration or adjustments of threshold and manual remodeling of geometries. With Parameters, there is no need to do anything like this. So design cycle much shorter. And design component, especially for low volume production, have quite significant effect on the total cost of the project. So as a result, because design fully automated and shorter, also the cost of the project is order of magnitude shorter. And design quality is much better than human created design. As an experienced engineer, I can tell you that human intuition works well maybe for simple beams in one load case, but realistic result design cases have multiple load cases, sometimes many load cases. And human intuition does not work well on cases when we have many different load cases, especially if we have vibration criteria or we have fatigue criteria, stress criteria. Human intuition doesn't work there, and typically designs generated by our algorithms much more effective. Now, generative design associated very frequently with additive manufacturing, and it's clear why. First of all, in additive manufacturing, we have nearly complexity is free. It's not exactly, but we are very close to what we call complexity free. We can realize very complex shapes. And traditional CAD is tailored for traditional manufacturing. So in order to realize the complexity, we need new design tools which can create this complexity. And definitely CAD is not there. We need generative design tools. Second, which is very important, it's also part consolidation, which leads to more effective supply chain. Of course, lightweighting and high performance. So you can see this is an example we ran with Airbus a few years ago. Hydraulic manifold, the original one was just block of material with a bunch of holes. Flow wasn't good and it was heavy. Alternatively, it was many channels that need to be consolidated and connected. And in order to have very effective design here, we needed to go into resolution of 60 million elements. It's like 180 million degrees of freedom, and design was generated very effectively, and it was manufactured. I already mentioned that CAD is deficient, especially for additive manufacturing. And typically, if you decide to go for additive manufacturing, it's better just to redesign. It doesn't make sense to take traditionally designed part and to 3D print it. We need to redesign for additive. We most likely will get lighter solution, better quality. We can save material, we can get better designs. And even if user knows it, look at this tremendous complexity, which was printed both in metal, in plastics. This tremendous complexity, even if assuming engineer knows how this design should look like, just to reproduce this geometry in CAD, nearly impossible. So this is the power of generative design here. And what industries are benefiting from generative design? I think it's very much clear when we talk about lightweighting. First of all, automotive, we have many customers from automotive industry, especially automotive going through changes, significant changes in terms of electric vehicles, lightweighting, redesign of many components. Aerospace, of course, every kilogram, if you look at lifetime of the airplane, flying all the time, hopefully after Corona period, we will have flights back again. Of course, reduction of every kilogram of weight plays a lot of role. Space taken each kilogram to orbit costs a lot of money. Medical customization, robotics, and industrial design, these are primary industry. There are other industries, but these, in our view, we address right now most of these industries in the current point. All right, I would like to go and shortly show how software looks like. We don't have enough time to run a full demo, but I would like to show how it looks like. So Cognicad is our software platform. It's available, until now it was available only as cloud service. Basically we run on AWS and Amazon Cloud. And access was available via a browser. We are also releasing now local Windows version for those who have some security concerns or limitations. They're also able to use a local Windows version. So I will run like a short demo here on our cloud version. So you can see this is our typical Cognicad view. So the software, it's running on the browser. User just need credentials to sign up, and they have tokens to run design. And you can see the platform is built the following. We have generative design component for mechanical and thermal systems. We have some reverse engineering component, and we have also design of support structures and slicing component. So the way the flow works is that users import step file. So we need to provide, I have open model here. So we need to provide the software with available design space. And when we design a part, some areas around, let's say around whole ball bearing area should be preserved untouched by the algorithm. So we need to prepare still in CAD some available design space and import this assembly into Cognicad. Now we created flow, which is very intuitive, and we believe that learning curve is really not steep. It's very intuitive flow. When user need to go through a few steps to set up a problem, so let's set up a problem together. So first, user need to define material properties, assuming this is, we have quite a wide library of different materials here. Once users select material properties, let's say aluminum, you can edit these material properties if you think they're not correct, or save some material properties. Next, we need to classify among the assembly what is our design space and what are non-design features. Non-design features is basically the areas that should be preserved untouched by the algorithm, right? So we would like to keep all these ball bearing areas to be untouched by the algorithm. So basically we need to classify it in such a way. Right, I hope I didn't miss anyone. And so a few words about this part. So we would like to design a component here, which is mounted to the base here, and is carrying a weight of some GPS and camera. Okay, so this is an idea. And then we have next step to define loading conditions. So we support vibration, normal modes, or static load cases. And typically the way it works, I'll define a new static load. We need to define boundary condition, basically how part is fixed against movement, against an XYZ orientation, or we can also allow rotation. And we need to define loads. So for instance, if the component which has some weight applies load, so the way it works, we can select just these 4 objects, and we can put center point in the center of mass of this object, and we will apply a load. I think we don't see the load, you see the tip of the force here. Once we click apply, it will calculate the equivalent loads. So a typically user can define forces, he can define moments, he can define pressure loads, we can define acceleration, g-forces, quite wide variety of loading conditions. So in this case, I defined 3 load cases, basically loads in direction X, acceleration in direction Y, in direction Z. And last step is to define the goal, what we would like to achieve. So for vibration load cases, typical formulation is to maximize eigenfrequencies, normal frequencies. For static load cases, we typically want to either maximize part stiffness. It's in our jargon, we say it minimum compliance problems. And in Cognicad, you can put weighting factors for each load case. And we need to specify volume fraction. So here it's more or less like guessing. User have to guess what's the volume fraction and come to iterations. This is nice for exploration, but it's not to solve the real engineering problem. So to solve the real engineering problem, you need to address the second formulation. Second formulation is basically saying, let's minimize mass under stress constraints. At the end of the day, this is what we want. We want part to be lightest as possible such that it doesn't break. So considering that we talk here about material like aluminum, which has yield stress of 230 megapascal, and given situation that this model can be under fatigue, we would like to limit stress to 80 megapascal for each load case. Of course, different stresses can be addressed for each load case. If you know the stiffness, because sometimes models for low stress, they not super stiff. So user can also change add stiffness constraints even. And the last point is to define either its investment casting or additive manufacturing constraints. Next is a resolution. Resolution, we talk here about finite element resolution behind the algorithms. Low, approximately 500,000 elements. Medium resolution, it's approximately 2.5 million elements. And our high resolution, it's approximately 10 million elements. So we work on very high resolution. We developed our own FEA solvers, which scale very well on the cloud. And user can also select the speed. As speed goes up, more computations needed. And basically, you just need to hit design. Once you hit design, it will take some time to run. You typically can take from tens of minutes up to a few hours, and design is ready. So this is a solution for formulation of, let me see. So that was exactly the formulation that I showed to you to minimize mass under stress constraints of 80 megapascal. So this is a model that we get. So we can hide, and you can see the model is smooth, watertight, STL model. We can take it directly to the printing. There is no need to do any modification, any thresholding. This is just ready for manufacturing. Just to confirm that the model is viable, we can observe the stresses. So we see that for the first load case, let's see, for the first load case, which was like this, we can even simulate the deformation. For the first load case, stress is 71.6 megapascal. For the second load case, it's 73.5 megapascal. And for the third load case, 72. So they all below 80, very close to 80 megapascal. So in all these three load cases, structure is viable, and it is ready for, we can take it directly to manufacturing. So if we want to download, we can basically download the model and just want to download it live and open it. You will see the quality of the STL mesh. Open it here. So you see the quality of the STL mesh is very high quality, and it is watertight model. It is ready for manufacturing. We just can send it further to supports or to printing. So the model is available as STL model, and we also, it's available as a step file. So we do notification, so model is also available as a step file. I also have slightly different formulation for the same problem. For the same problem, I also had the formulation of for vibration load cases. If you would like to maximize the normal modes, to maximize the eigenfrequency for the same part, design, of course, will look slightly different. And this is exactly where, where human intuition probably does not work well. So for example, this is a design for to minimize mass to maintain the stresses. But this is a design we would like to maximize the frequencies, the eigenfrequencies of the model if we care about vibration of this part. And we can even look, you can see how vibration mode looks like. So the first mode is 223 hertz, second was 252 hertz, and third 283 hertz. So this is the first mode, this is the second mode, and the third mode. So those of you who are more familiar with topology optimization, it's very typical and actually a big problem for many other software for maximizing eigenfrequencies, because modes become closer, and that's where all solution fails, and this is where parameters really shines in these terms. So then if we have the design, let me close not to make it too heavy. So once design is done, we can also go and generate support structures for the same model. I already pre-generated, just wanted to show what capabilities Cognicad also allows. So typically users have to import STL file. They have to choose the orientation, either manual orientation or to ask algorithm to find the optimal orientation to have minimum supported surfaces. User can define overhang angle, unit cell size. There are several parameters which user can address, and also for slicing the layer thickness. And again, one-click solution, all these support structures were generated, and user can control the thickness of beams, the thickness of the tip, how much it penetrates inside the body. And this is what we have, very high quality support structure that we have so far. And in all evaluations, we performed very well. So I think maybe I took a little too much time, so I will go back to presentation. I will be happy to address some questions later. And quickly, Eric, do we have a few more minutes for me?
Yeah, we can cruise through this and then get over to additive manufacturing, and then we can address. We have a couple questions.
Great. Just I would like to show 2 case studies, and we can go back to you. So as a case study, I would like to show a few cases that, to show that it really works. In parameters, we're not about creating only cool shapes, we're about solving tough engineering problems. And I would like to show these examples here. So first one is in motorcycle industry, together with a company called Ecos and Renishow. We redesigned a component which was mounted to the frame. It was holding 2 cylinders which were moving, vibrating. It was quite a tough situation, so we completely redesigned the part. It was additively manufactured by Renishow, post-machined as needed, and it was a very successful project. Not only that we could reduce weight by 35%, due to fatigue, stresses were supposed to be much lower then it was 3.5 times lower than yield stress. We achieved significant stress reduction, and also in terms of natural frequency part as well. So it's a very successful design in these terms. And another case I would like to show is that this case shows where really Industry 4.0 that we talk about really shines. How you can design suspension, design suspension, and manufacture this suspension for automotive within 5-6 weeks. How it is possible? Because typically just design cycle would take a lot of time. So we partnered with Archimoto Exponential Works to redesign several components, including the swing arm, upright, A-arm, and some pedals. Overall, it was 5 or 6 pieces that we needed to design. And design cycle took 6 days, but most of this time it took CAD work to create just design spaces, to go into assembly to find the available design space. And we redesigned these parts. Some of these parts were 3D printing, some of them were investment casted. It's actually a very interesting and effective process where you 3D print sacrificial part, create sand cast mold, melt out the plastic, and then cast aluminum inside. Also hybrid manufacturing process, which is very, very effective. We could achieve significant lightweighting between like 35 to 50%. And designs were very also cool looking, but they also were viable in terms of engineering performance. And yeah, it was a very successful project, and this is where it shines. And looking into automotive industries, which is going through many changes recently, it's very important to address and to understand that there are tools today which will allow companies to be very effective and productive. So I think, yeah, maybe here I will stop sharing. We'll go back to you, Eric, and yeah.
Yeah, and now for more on manufacturing your generative design. So why additive manufacturing for generative design? You're able to achieve complex geometry, complex geometries that you're not traditionally able to achieve with something like CNC. So this is lattice structures, manifolds, things with internal geometries. And because of this, you're basically able to do what they would say is unmakeable optimized geometries or generative design. And Michael did touch on this a little bit, but also part consolidation is able to be achieved with additive manufacturing. Take, for example, kind of like a pump impeller. Traditionally, that would need to be manufactured in several parts and then welded together. With additive manufacturing, you can actually print them all together, and then you kind of reduce the weld points that would present some kind of structural issues potentially. There are some other considerations that you will need to take into account. AM can be expensive, just depending on the type of technology and what you're trying to achieve. But really, you kind of need to do an internal kind of analysis of this. Other things to take into mind are lead time and tooling costs, and how fast you're trying to get to market if you were doing kind of the traditional manufacturing. Another thing to keep in mind is also the size of your part. 3D printing is getting a lot bigger in terms of the units and the build volumes that they're able to achieve. But that's on a technology basis. I know that Big Rep has a FDM machine that's about 1 meter by 1/2 meter by 1/2 meter, and there are some larger options out there. There's 2 ways that you can manufacture your parts with 3D printing. There's direct to 3D print or 3D print directly. So here's a longboard truck created with desktop metal, but also you can do investment casting. So this is, you print the positive using a PVB. I think there's wax materials as well, and then they're coated in a ceramic material. The material is burned out, and then it's filled with the metal that you want. A little bit on the technology. So these are 4, well, actually 3 processes, and then there's metal printing. These are 4 of the commonly used ones. You have material extrusion, which is just basically heating a strand of thermoplastic or composite material. That photopolymerization. This is a light source is used to project into a photocurable resin layer by layer. We have powder bed fusion, where either a laser or a heat source is used to fuse particles layer by layer, and then a new layer of powder is put over that. And then we have metal printing. Metal printing is not one of the ASTM defined additive manufacturing processes. It's actually achieved, there's material extrusion, there's binder jetting, there's direct energy deposition. In terms of how these can be used, on the material extrusion side, concept validation, some end use, and like I did say, investment casting. So I think Polymaker has a PVB type material that can be used. It burns out almost 99.9% ashless. On the photopolymerization side, same thing here is concept validation, some end use, and investment casting. For powder bed fusion, concept validation, small production runs, end use. I'll get into that a little bit more here, and then obviously with the metal, it's mainly end use. A little bit on the pros and cons of these. with material extrusion, you're going to have a large material selection. So you have anything from investment casting materials to TPEs, TPUs, carbon fiber and fiberglass composites, and all the way up to kind of PEEK and PEC. Those are obviously up on the higher end in terms of material properties. On the cons, they do have, there's a trade-off between surface finish and the amount of time it takes to create your model. And then also materials or your designs can be orthotropic. So you do have some weakness along layer lines. You will get strength in one direction, and then other directions you really fall short. That photopolymerization, you're going to get a smooth finish with these, almost injection molded quality. Very highly highly accurate and detailed. I think it's about 25 microns on the XY. Parts can be brittle though, and these materials are UV sensitive, so extended exposure to UV light will make these more brittle over time. For the SLS or the powder bed fusion, a great thing about this is you're able to do lots of parts in one build volume, so you're printing multiple parts. Great material properties on this side, but there are very few materials for the SLS side. And then lastly, metal. Great thing here is no machine labor required, as well as no tooling. The cost and time can really add up. There are limited materials, and startup costs can get high on the metal side. Some of the materials out there right now is they have 17.4, 316L, H13 tool steel, 4140, and copper, and they are adding to that continually. A little bit about Dynamism. We're a brand agnostic reseller of 3D printers. We are able to recommend the best technology for your application. I've put a few options here for each one of the technologies that I did talk about. Ultimaker is a great kind of prosumer desktop for material extrusion. And next I have Nexa for vat photopolymerization, which is actually a really interesting option. It's one of the world's fastest 3D printers at 1 layer per second. And it also has an extremely large build volume compared to a lot of the other SLA and DLP brands. Also on the vat photopolymerization, if you're looking for more of a desktop option, the Formlabs is a great option as well. Powder bed fusion, that's the SLS, and then desktop metal. I'm sure lots of people have heard about them. They have a variety of options depending on if you're trying to do just one-off prototypes, or you're actually looking to move into full-scale production using additive manufacturing. And with that, I think, oh yeah. So yeah, if you are looking to get started with generative design, we're going to be sending a follow-up email after this. It's going to have a link to Parameters so that you can optimize your own part. And if you would like to get that design printed, let's say you don't have a 3D printer currently, you are more than welcome to contact Dynamism, and we will print that part for you. If you have an extremely large part or you're looking for something like metal, those can be done. We would just have to talk about additional costs, just depending on the part. But yeah, we can go ahead and take it over to Q&A. I know we had a few for Paramatters directly. Michael, so is your software able to integrate with Onshape?
No. No. Well, there's our software can be integrated with any CAD tool in terms of you can take any CAD tool can export step or STP format, which is, I would say, neutral to any CAD system, and you can import it into Cognicad. With Onshape, we had plans, but they were not realized. So we don't have a direct integration. Meaning, if you want as one click to import model into Cognicad that doesn't exist. You will need to save it on your machine and import into Cognicad, which takes another 20 seconds. But there is no like direct integration. No. Right now, Cognicad is standalone tool, which works with all standard formats. Import as step file. The output can be both step and STL, so it can be agnostic with any machine, any system.
Okay. And as you were doing the Cognicad walkthrough, there was the comment made, so you had the very long list of materials. Does Cognicad have 3D printer materials as well?
Yes, more 95% of all this list are 3D printed materials, started from plastics to metals. Currently, we consider isotropic materials, but in future we will also consider anisotropic materials.
Yeah, so we have some questions about the subscription model and the price. Would you mind clearing that up for us?
Yes, so as I said, we're also releasing now Windows local version. So Windows local version is typical licensing model. For the pricing, you can address either to Dynamism or to us for the pricing. Regarding the cloud version, it's basically a cloud service. There is no cost for software. We charge per computational design. As I explained, generative design is quite computationally expensive process in terms of heavy calculation. That's why we run all these processes on Amazon Cloud. So we charge proportional to the computational effort needed to solve the optimization problem. And as I mentioned, there is no cost for software. Users purchase package of tokens, and these tokens are deducted from user's account proportional to the usage. And when I say proportional to the usage, means depends on how many load cases, what's the resolution, what's the formulation. Before running the optimization, users can see how many tokens will be deducted from the account prior running the optimization study. And we offer several packages, very affordable prices, packages of tokens.
Okay. We have quite a few questions here, so if we don't get to it, we are going to get to that in our follow-up email, just so we take care of everyone here. I have a couple really good ones here. So does Parameters have the capabilities to produce generatively designed lattices or metastructures? Someone specifically looking to generate oxidic bending dominated lattice to maximize shock absorption and vibration dampening?
Yeah, well, it's a good question. There is a lot of excitement, with not saying hype, about the lattice structures. From our engineering understanding, lattice structures may look nice from engineering point of view, structural performance point of view. They're not as effective as people think. We use lattices where they needed to be used, and you could see our support structures. We use lattices to generate support structures. This is where it makes sense. From engineering point of view, our topology optimization design will generate much more effective structures than lattices, and it was quantitatively improved. So lattices, we can do it. We don't do it because we target solving real engineering problems, and we use lattices for supports where it's needed. Of course, we will consider if we need to use it in the future, but so far, our topology optimization, mesostructural optimization generate much more effective structures than lattices in terms of weight versus performance.
Okay, we have another one here on the 3D printing side. So which material and 3D printer would you use to print the mold for investment casting process? It just depends on what you're trying to do here. If you have something small and highly detailed, let's say jewelry, something like that, Formlabs has a casting material, but there is a limitation on build volume there. outside of that, Polymaker, they have a polycast, or it's a PVB type material. I have used this personally, and the casting house that we talked to, they were blown away by the ashless burnout. Uh, Traditionally, people have tried things like polylactic acid or PLA on material extrusion, but that can leave a lot of residual kind of burnt plastic into the mold. So that PVB, that polycast, is works really well for the FDM side. And so if you are looking to do something bigger, you can do the Ultimaker S5, I believe, with Raise 3D, or even up to, I know Big Rep is open filament format, and so that's a meter by a half meter by half meter. So you can do pretty big options with that PVB material.
If I may add, we also had all the customers that we work, we had some experience. So we also used voxel jet for SLS technologies. They also have pretty good quality.
Okay. So Michael, you mentioned that post-generation corrections and modifications are not needed. But if in that case, the mesh form of the generated model is to be post-modified for some reason, is it possible, and does the software have a possibility for it?
Yeah, so we actually, one of the unique features of our algorithm is that, first of all, it converges to very discrete design. The reason why other algorithms require post-working, because they don't converge. This is just, our algorithms converge very well. They have very robust feature size control, so they're manufacturable. We do not offer editing tool. If for some reasons users want to make changes, they would need to go to some editing tools, which there are plenty of free or not free on the market. Even like FreeCAD, you can go into some editing. We do not offer. We specifically target to create very strong tools which will generate viable designs. If for some reason you need to make changes, you would need to do it in another tool, but please remember that if you will make changes, they may affect structural integrity, so reanalysis, rerun finite element analysis will be needed here.
Okay. I got enough time for maybe one or two more, and then, like I said, we will follow up here after the webinar with a recording with additional information, and then we can also get to some of these extended questions. What gives the generative design such an organic, complex shape? Are there any options to generate designs with sharper facets or more minimal aesthetics?
Yeah, it's a good question. It's to address it completely. It's a long answer, but let me try to answer in a short way. In CAD, you have what is called parametric design. You create shapes based on some parameters, right? Some parameters will create given shapes. In generative design, I would call it free form. Why free form? And the way it works, you have your domain, you divide it by elements, and you allow algorithm put material where is needed. So in many cases, it's not connected to parameters. Now, this is the first. Second, as I said, it's physics driven. The way it works, we solve system of finite element equations, and then optimizer drives result into given point. And typically, the goal to minimize stiffness or to limit stress or to maximize frequency, typically these structures want to avoid sharp corners. And sharp corners is a place where high stress concentration will be expected. And the organical component comes from the situation when just algorithm want to avoid all sharp corners and to have very smooth surfaces to minimize stress concentration. Hope it's clear. If not, I can answer later.
Yeah, I think that's about enough questions. Apologize if we didn't get to all of them. We had almost 20 questions here. So we will be following up with more questions after this, as well as, like I said, a recording and and also links to try out Paramatters and have that printed. Yeah, I appreciate the time, and everyone have a good day.